On November 10th, a new update from observatories stunned the community. After its latest swing past the sun, 3I Atlas appears to have quite literally left some of itself behind. Post-perihelion tracking suggests it dumped around 13% of its entire mass into space, on the order of 4 billion tons of rock, gas, and frozen material lost in just a few days. According to standard comet physics, an outburst that violent should paint the sky with a colossal tail, a bright, ragged streamer of dust stretching millions of kilometers behind the object. Yet when China's Tianwen-1 spacecraft pivoted away from Mars and locked onto Atlas, the pictures it sent home told a very different story. Instead of a shredded plume and a long, dramatic tail, the images showed a small, hazy ball of light. No obvious debris. No sweeping trail. Just a compact, ghost-like glow. So where did those billions of tons actually go? That missing mass has now been logged as the 10th major oddity in Atlas's behavior. In all, researchers count 10 separate features that don't line up with what we've learned from thousands of ordinary comets. When the odds of each quirk are combined, the chance of all of them happening in one object by pure luck falls below 1 in 10,000, and may be closer to 1 in 100,000. That leaves astronomers staring at a hard question. Are we looking at a wildly extreme natural object unlike anything seen before, or does this pattern hint at something our current theories simply aren't built to explain? What we know so far exists only because a lone probe around Mars was told to look somewhere it was never meant to. While ground-based telescopes chased other targets, China's Tianwen-1 received a quiet change of orders. Stop mapping Mars, the world it has circled for years, and instead aim its sensors at an object racing tens of millions of kilometers farther out. That new target, moving faster than any regular body in the inner solar system, was 3I Atlas. It was slicing through space at roughly 58 kilometers per second, about 129,000 miles an hour. At that pace, it could loop around Earth in less than 20 minutes. Its solid nucleus, about 5 to 6 kilometers across, was comparable in scale to a city, but far darker than fresh asphalt and colder than hardened steel. Tracking something that tiny and that faint pushed Tianwen-1 right up against its limits. The orbiter was built to map large, bright, mostly steady terrain. Now it had to hold a lock on a dim ember drifting across the stars faster than its targeting software was ever designed to follow. For weeks, engineers on the ground tuned and retuned the guidance systems, knowing that the slightest pointing error would cause Atlas to vanish into the background. In the end, the work paid off. China's space agency released a sequence of raw, black and white images showing a faint core wrapped in a soft, expanding shell, the coma of Atlas stretching thousands of kilometers into the dark. Those frames were crisper than anything we've seen through Hubble, cleaner than what James Webb can deliver through Earth's line of sight, and free from the blur that plagues even the best ground-based observatories. For the first time, humanity had a clear, close-up portrait of an interstellar object in motion. Atlas stopped being just lines on a graph and became something you could almost picture in your mind, a real, three-dimensional body with light, shape, and texture. But hidden inside that achievement was a contradiction. The glow surrounding Atlas looked unnervingly calm. There were no ragged jets, no spiky fans of vapor, none of the chaotic streaks normally carved by gas boiling off a sun-heated surface. Where models predicted turbulence, the cameras showed smoothness. Where we expected broken streamers of light, the halo shimmered evenly, as if the whole object were exhaling in one slow, controlled breath. A masterpiece of engineering had revealed a paradox in nature, and that paradox is where the deeper mystery began. Near its closest approach to the sun, something subtle but measurable happened. Atlas began to shift away from the path that gravity alone would have set for it, as though a faint extra force had joined the tug of the sun. Teams at NASA's Jet Propulsion Laboratory confirmed that 3I Atlas was experiencing so-called non-gravitational acceleration, a tiny, persistent push usually caused when material leaves a body fast enough to nudge its orbit. The numbers themselves were clear. At roughly 0.9 astronomical units from the sun, Atlas showed a slight outward acceleration on the line between it and the sun, and a smaller sideways component along its track. When those values were run through the equations of momentum, they all pointed back to the same answer. The object must have dumped close to 13% of its mass, on the order of billions of tons, in a remarkably short time. By all our expectations, that kind of mass loss should blaze as a bright, dramatic tale. Yet Tianwen-1, ESA's Mars Express, and telescopes on Earth all reported the same view. A small, steady ball of light, no broad spray of dust, no obvious fan of gas, no sign of violent activity. The extra push was real, but any visible exhaust was missing. Instrument glitches were the next suspect, but one by one those were ruled out. Different spacecraft, different detectors, and independent analysis teams all measured the same change in motion. Atlas had clearly been pushed, but whatever carried that push left no obvious trace in the images. It was as if a thruster had fired in complete silence, with the exhaust somehow erased as soon as it left. For many researchers, this became the first clean, well-documented case where the math demanded a force that the cameras could not see, a separation between what the equations insisted on and what the images revealed. And the strangeness didn't end there. From the moment Atlas crossed into the solar system, its route looked oddly familiar. Interstellar visitors are expected to arrive from almost any direction, with orbits tilted at wild angles to our planets. Atlas did not. It slid into our neighborhood almost perfectly lined up with the ecliptic, the thin orbital sheet on which Earth, Mars, Jupiter, and the other major planets circle the Sun. Measurements show that its orbital plane is offset by only about 5 degrees from that same disk, small enough to fit comfortably within the scatter of native solar system objects. That by itself set off alarm bells. Bodies that share the ecliptic are usually assumed to be local, born from the same flattened cloud of gas and dust that built our planets. Atlas, by contrast, was flung out of some other system altogether. Statistically, it ought to have come in on some steeper, more chaotic path. Instead, 3I Atlas skimmed in almost flat, tracing a line that mirrored our planetary layout, but moving the opposite way. It traveled backward through the traffic lane, retrograde yet still confined to the same narrow sheet. That pairing coplanar and counterflowing is not just odd, it's incredibly precise. Imagine a single leaf gliding along the exact surface of a fast river, but drifting upstream without ever sinking below or popping above that surface. The odds of that happening by accident are very small. If objects from deep space truly approach from all directions at random, the chance of one entering within 5 degrees of the ecliptic is only a couple of tenths of a percent, roughly 1 in 500. On its own, that could be dismissed as an unlikely but possible fluke. Stacked on top of Atlas's other 9 anomalies, it becomes one more piece of a puzzle that refuses to sit comfortably inside any model we currently trust. Teams ran the orbit solutions again and again, convinced that the early fit might be warped by short tracking arcs or noisy data. But every fresh attempt from JPL, from ESA dynamical groups, from Chinese flight analysts landed on the same picture. The path was correct. The tilt was correct. The geometry held. And yes, the object really was sliding through the same orbital sheet as our planets, but in reverse. 3I Atlas wasn't just close to the plane of the solar system. It was moving through the very layer where our worlds circle the sun, but heading the opposite way, like traffic flowing backward along a one-way highway. That's not something standard ejection models produce easily. Material kicked out of distant star systems is usually scattered at all sorts of angles by violent gravity encounters. For Atlas to arrive almost perfectly level with our ecliptic suggests either an outrageous stroke of luck or some larger pattern in how debris migrates through the galaxy that we haven't mapped yet. Some theorists suggested a hidden population of interstellar rubble, a broad stream of fragments roughly tracking the Milky Way's midplane. In that scenario, Atlas might simply be one piece following that unseen river, but so far no one has found convincing evidence for such a flow. Others went a step further and asked the uncomfortable question, what if the alignment isn't accidental at all? What if the path was chosen to cut through the planetary plane on purpose, maximizing close passes, gravitational nudges, and observation opportunities? For many scientists, the emotional punch was hard to shrug off. The ecliptic is more than a plotted line on a chart. It's the floor of our cosmic home, the stage on which every familiar planet moves. To see a stranger enter on that same level, perfectly straight yet going the other way, felt like watching a foreign signature written in our own script. You didn't need wild theories for it to be unsettling. The orbit's sheer neatness, too tidy, too exact, was enough. That alignment became the first solid fracture in ordinary orbital dynamics, the moment when standard terms began to feel too small, and Atlas started its quiet rebellion against randomness. Then the object broke an even more basic rule. Between July and August 2025, observatories on multiple continents recorded Atlas doing something no comet had ever unambiguously been seen to do. It fired a jet of material directly toward the sun. Not away from it, straight into the glare. Everything we teach about comet behavior says that's impossible. Sunlight warms the surface, trapped gases expand, dust is lifted, and solar radiation together with the solar wind push that material outward, carving a tail that reliably points away from the star. The effect is so dependable that astronomers use the tail's direction like an arrow to find the nucleus. Atlas ignored that arrow. Its strongest outflow wasn't retreating from the sun, it was driving into it. At first, the obvious explanation was geometry. Under special viewing angles, a normal tail can appear reversed, an anti-tail illusion that occurs when Earth passes through the comet's orbital plane. But telescopes in Chile, Japan, and Italy, all looking from different positions, reported the same orientation at the same time. The three-dimensional geometry didn't line up with a simple trick of perspective. Atlas really was throwing material toward the star, straight into the stream of radiation and charged particles. That directionality makes no thermal sense. For a natural vent to point sunward, the rotation of the body would have to be so extreme that centrifugal forces might tear it apart, and even then the escaping gas should be almost instantly bent backward by the solar wind. Instead, the jet held its aim for nearly 48 hours, a full 2 days of steady, sun-facing flow. A few teams suggested that the interplanetary magnetic field might be channeling the particles along twisted field lines. But near 1 astronomical unit, that field is far too weak and too disordered to carve such a sharp, persistent beam. Others imagined a deeply buried cavity-focusing gas through a narrow opening, like a natural nozzle. That might explain a tight jet, but not its ability to resist being swept back for so long. On the plots, the behavior looked less like random venting from a crack and more like controlled exhaust, as if a nozzle were deliberately keeping its aim. That implication made many researchers deeply uneasy. The picture of a lone object actively pushing against the sun's wind felt almost mythological, like watching a traveler lean into the strongest gale in the system and refuse to turn. It wasn't just poetic, it was physics acting as though the usual rules were optional. In the official catalog, the event was captured in a bland line of text, a jet oriented along the solar vector. But buried in that neutral phrasing was an unspoken realization. Some process was operating with a level of directional precision that looked uncomfortably like control, not mere evaporation. Atlas wasn't just being pushed around by sunlight, it was threading its way through it. For as long as we've watched comets, their tails have streamed away from the sun like smoke from a fire. For reasons we still can't fully decode, Atlas turned to face the furnace and pushed into it. The object itself was anything but small. With a core roughly 5.6 kilometers across, 3I Atlas was comparable to a drifting metallic metropolis wandering between stars. That scale alone put it in a different class. Its speed made it stranger still. Moving at about 58 kilometers per second relative to the sun, around 129,000 miles per hour, Atlas ranked as the fastest object of its size category ever tracked. In nature, there is usually a trade-off. Tiny fragments can be accelerated to extreme speeds by close encounters and gravitational slingshots, but big bodies tend to stay tethered to their home systems. It takes an enormous amount of energy to hurl something that massive into interstellar space. Atlas broke that pattern. It wasn't modestly large and moderately quick. It was both huge and exceptionally fast. For context, ejective Oumumu, our first known interstellar visitor, was a slim, maybe 100-meter scale shard. Borisov II was a more typical comet just a few hundred meters wide. Atlas towered over both, estimated to be more than 1,000,000 times heavier than ejective Oumumu, and roughly 1,000 times more massive than Borisov. By standard statistics, an object like that should be exceedingly rare. Yet the third interstellar object we ever noticed turned out to be the biggest and one of the swiftest. Current models of how things get flung around the galaxy don't like that combination. High-speed ejecta are expected to be small scrap from violent events. Larger bodies are supposed to stay bound. To give something with Atlas's mass the velocity it carries would require either a truly catastrophic gravitational encounter, say, a brush with a neutron star or black hole, or some kind of directed push. Neither option fits comfortably inside everyday probability. Researchers tried to domesticate the numbers. Maybe they had overcounted the effect of the sun's gravity folding an extra acceleration. But even before entering the inner solar system, Atlas was already moving faster than typical interstellar escape speeds. Perhaps it was part of a larger hyperbolic swarm, a family of objects sharing a common past. If that were true, we should see other bodies on similar tracks. We don't. Atlas moved alone, ignoring the distributions we'd expect. Behind closed doors, some astronomers started using a telling phrase, a statistical rebellion. Every curve and probability map agreed that an object like Atlas should be almost impossible, and yet it was right there, carving through the solar system like a projectile launched from beyond our charts. That naturally raised the next question. Was this truly a freak of nature, or did its trajectory bear the fingerprints of a deliberate departure? The formal anomaly report captured the situation in technical language, noting that the object showed an extreme coupling between its mass and its velocity that didn't match random ejection scenarios. In everyday terms, it boiled down to this: Atlas is too large and too fast to be where it is by ordinary chance. A natural object might violate one expectation. This one seemed to ignore at least two. Its path through the inner solar system only deepened that sense of intent. Atlas didn't just drift in on a random route. It traced a corridor that looked oddly matched to our observation network. From the moment it crossed Mars's orbit to the point where it skimmed the outskirts of Jupiter's realm, its timing lined up again and again with when spacecraft were awake and looking. In September 2025, Atlas passed near Mars at a distance of only tens of millions of kilometers, ideal for high-resolution imaging. Right then, by coincidence or design, ESA's Mars Express and the Trace Gas Orbiter were both well-placed and operational. A few weeks later, Atlas's path took it near Venus during a period when probes there were also gathering data. Later, it slid past the far edge of Jupiter's gravitational influence, close enough for remote sensing, far enough to avoid a major deflection. Each encounter was both geometrically neat and conveniently timed, as if the object were stepping through a series of pre-planned marks. Alone, all of that could still be written off as luck until perihelion. When Atlas reached its closest point to the Sun at roughly 0.9 astronomical units, it should have been at its brightest as seen from Earth, the perfect moment for intensive study. Instead, at that exact time, the Sun sat directly between us and the object. From our planet's point of view, Atlas vanished into the solar glare. For several weeks, every ground-based observatory was effectively blind along the line of its path. The one window when our instruments should have seen this visitor most clearly became the window where it was completely hidden. Calculations put the odds of such an exact solar conjunction happening right at peak brightness at roughly 1 in 20,000. It felt less like simple bad timing and more like the universe shuttering the stage at the climax. From other perspectives, however, the target remained in view. From the orbit of Mars, from the neighborhood of Venus, from the distant watch of Jupiter's domain, Atlas stayed observable long enough to be recorded. Earth alone sat in the dark. To spacecraft designers and mission planners, that path looked almost optimized, a route that grazed multiple outposts in space while avoiding the most heavily instrumented vantage point. Officially, the event was summarized in neutral terms. The object became unobservable from Earth due to solar conjunction at perihelion. Between those lines, many sensed something more. Atlas had effectively pulled off a perfect disappearance act at the one moment we most wanted to see it. For some in the field, that was the turning point, the anomaly that made simple coincidence feel much harder to defend. The composition story only added to the unease. When scientists dissected the comet's light in mid-2025, they expected the usual comet chemistry: plenty of water, assorted carbon compounds, silicate dust, and a familiar metal mix. Instead, the spectrum was dominated by metal, and one metal in particular: nickel. In most comets, iron leads and nickel follows. That ratio is so regular that it's considered part of the chemical fingerprint of our system's birth. Atlas flipped that script. Nickel lines flared stronger and sharper than iron. The nickel-to-iron balance didn't just tilt, it appeared to reverse. Where typical cometary material is iron-heavy, Atlas seemed defiantly nickel-rich. On top of that, the spectra showed powerful signals from nickel cyanide molecules, at levels far beyond anything seen in other comet comas. Depending on the exact model, their abundance appeared to be tens to hundreds of times higher than expected. The anomaly was so extreme that at first, teams at ESA and JAXA assumed their instruments were being fooled. After repeated recalibration and cross-checking, the conclusion stood. The signal was real. That forced theorists to ask what kind of environment could produce such a body. Maybe Atlas formed very close to a hot, old star where heavy metals dominated and lighter elements were boiled away. But even that kind of nursery doesn't easily explain such a clean, nickel-forward spectrum. In our standard formation models, you don't get that kind of extreme tilt toward nickel without dragging along other markers with it. Atlas's chemical fingerprint looks strangely pure, almost selective. On the record, researchers labeled it non-standard metallic enrichment. Off the record, many admitted what the plots suggested to them. The composition didn't just look unusual, it looked, in some deep way, as if it might have been chosen. In laboratories on Earth, that strange nickel-iron imbalance set off a quiet alarm. The same kind of ratio shows up in advanced nickel alloys, the metals engineers choose for spacecraft hulls, turbine blades, and thermal shields, precisely because they shrug off corrosion, cracking, and savage temperature swings. The resemblance was hard to ignore. The spectrum by itself doesn't prove anything artificial. But if you were designing a shell or probe to endure millions of years drifting between stars, a nickel-heavy structure would be a very logical starting point. For a lot of astronomers, this was the moment the story shifted. Until then, Atlas's oddities could be filed under awkward geometry and bad luck, weird orbit, odd angles, strange timing. Chemistry is different, chemistry is identity. And now the makeup of the object felt uncomfortably close to our own engineering choices. For the first time, what we called natural began to look eerily familiar, as if the cosmos were writing in a handwriting we recognized. On paper, the language stayed cautious. Spectral results showed unusual nickel enrichment, inconsistent with standard comet formation environments. Behind that restraint was a shared realization. 3I Atlas did not come from the same stock as our local debris. It was harder, denser, and likely older, something fired in a furnace we've never observed or shaped by processes we don't yet know how to model. Then it broke another foundational rule. Atlas was almost dry. Where a typical comet is basically a frozen reservoir, a filthy snowball packed with water ice, this visitor was closer to a metallic rock dusted with frost. Spectral analysis indicated that only a few percent of its total mass was water. Most comets carry 10 to 20 times more than that. By our usual definitions, this barely qualifies as a comet at all. The first reaction was simple disbelief. Water is the engine of traditional comet behavior. It turns to vapor in sunlight, drives jets, and builds the glowing tails they're famous for. If Atlas contains so little water, what was powering the intense outgassing and the measured non-gravitational push near the sun? The numbers refused to cooperate. Explanations quickly split into rival camps. One idea was that Atlas formed in an extremely hot system where early heating boiled away volatile ices, leaving behind compact metallic cores wrapped in rocky shells. Another suggestion was that it began life more like an asteroid, later picking up a thin film of volatile dust while wandering through interstellar clouds. But even those stories strained under the data. Atlas didn't just lack water, it behaved as though it had been built never to depend on it. Natural comets degrade. They lose ice, crack under thermal stress, shed chunks, and eventually fall apart after multiple trips past the sun. Atlas did not. Even after losing billions of tons, its nucleus stayed intact. Its faint halo persisted. A body with so little ice should have come apart under the same heat that stripped away its outer layers. Instead, it stayed together as if it were meant to take damage and keep going. If water wasn't the primary fuel, then something else had to be driving its jets. Perhaps vapor from metal-bearing compounds, gases from silicate materials, or mechanisms we haven't yet put into equations. Whatever the source, it acted with remarkable steadiness and efficiency, sustaining activity for weeks around perihelion. It didn't look like random boiling. It looked like regulated release. That thought unsettled even veteran observers. Atlas no longer fit the picture of a delicate snowball from a distant star. It felt more like a hardened traveler, tempered over eons, stripped of anything fragile and left only with what could endure. The image that formed was not of a pretty ice globe, but of something optimized for survival. Awe and discomfort arrived together. Maybe what we were watching was an interstellar object engineered, not necessarily by hands, but by time, selection, and harsh environments to last. The official phrasing stayed mild: volatile fraction anomalously low, bulk composition inconsistent with standard cometary ice models. Between those lines, the real implication grew louder. A comet with almost no water is a contradiction. A nearly dry body that still vents, still accelerates, and still refuses to disintegrate turns that contradiction into a statement. Atlas might not carry oceans, but it carried something rarer: the ability to step outside the box we tried to put it in. Even the light it reflected refused to play by the rules. Normal comets scatter sunlight in ways we understand well. The reflected light becomes partly polarized. The waves line up in predictable patterns based on dust size, surface roughness, and composition. From Halley to Borisov, every comet we've studied has followed that same optical grammar. Atlas shredded that script. During its approach to the sun, polarimetric observations revealed an unusually strong negative polarization signature, a twist so extreme that no standard dust model could reproduce it. Instead of aligning in the familiar way, the light waves seemed to flip, as if one component had been damped and the other reversed. This wasn't a glitch. Telescopes in several countries and instruments riding in Mars' orbit all confirmed the same effect. Put simply, Atlas was bending light the wrong way. The implied surface looked far more compact and organized than any fluffy, dusty comet core. Some scientists suggested microscopic metallic textures, fused nickel grains, or ultrafine crystalline layers capable of inverting polarization. Others imagined an electrically charged dust coating, shaped by magnetic fields and acting like a gigantic natural optical filter. Those ideas remained speculative. In controlled experiments, strong negative polarization shows up only in narrow circumstances. Specific minerals, special angles, or human-made materials designed to manipulate light. Seeing it at this strength from an object millions of kilometers away felt like stumbling across a laboratory effect blown up to cosmic scale. In everyday terms, Atlas didn't just bounce sunlight back. It seemed to process it. The data curves looked less like the usual Comet survey plots and more like the graphs from laser optics labs. Smooth but not mirror-like, reflective yet twisted in a very particular way. The written summary stayed calm. Observed polarization, angle, and intensity diverged significantly from all modeled scattering scenarios. Between those words, many readers heard something different. This visitor didn't just bring odd matter and strange motion, it carried hints that our understanding of how surfaces interact with light is incomplete. By then, Atlas already had a list of impossibilities: a suspiciously perfect orbit, a missing tail, unexplained acceleration, and a metal-heavy chemistry no comet should have. The polarization results added one more line to that list. It changed how photons behaved. And among all the odd alignments attached to 3I Atlas, one echo from the past stood out. Its inbound corridor lined up with nearly the same patch of sky that once made a radio telescope operator scribble a single word in the margin. Wow. The match wasn't exact, but it was close, about 9 degrees offset in a sky full of other directions. The famous WOW signal detected on August 15, 1977 came from near Sagittarius at the hydrogen line frequency around 1420 MHz. It lasted a little over a minute and never repeated. That handwritten WOW next to the data strip turned a single spike into legend. For decades, its origin has stayed unknown. Then Atlas appeared, drifting in from a corridor that cuts through that same general region. Neither adjective Oumuamua nor Borisov came from there. In principle, an interstellar object can arrive from almost any angle. For one to barrel in from a narrow cone around the only sky patch tied to our most famous unexplained radio burst pushes the edge of coincidence. Some estimates put the odds below 1%. Researchers were careful not to overreach. Correlation is not proof. There is no direct evidence that the signal and the object share a birthplace. Still, within the small communities that study interstellar wanderers and strange radio events, the overlap became impossible to ignore. If the WOW signal really was some kind of artificial broadcast, a precise, narrow hello beamed across space, then Atlas seemed to be coming from roughly the same neighborhood. If the signal was just natural noise, the alignment was still uncanny enough to justify a second look. Radio arrays were turned back toward that region while Atlas approached, listening for any repeat whisper. None appeared. But the geometry alone, one event written in radio waves, another in polarized light and nickel, both tied to the same corridor, kept the question alive. Had we looked twice into the same long, silent lane of the galaxy, or were we simply seeing patterns in a sky where our instincts can't resist connecting dots? No one can answer that yet. What remains as Atlas fades back into the dark is the shared direction, one anomaly etched in a minute of radio noise, another in the chemistry and optics of an interstellar stone. Both point toward a part of the sky that still feels less like a solved map and more like an unopened door. For a lot of researchers, that sky overlap with the WOW signal didn't trigger fear so much as a strange chill, like hearing a half-remembered phrase repeated decades later in a different voice. By the time that connection was noticed, 3I Atlas had already broken our expectations about orbits, chemistry, and light. Now it seemed to trace its path through coordinates already stamped with the word mystery. The SETI network's official note did its best to stay calm. It simply stated that Atlas's incoming path passed within roughly 9 degrees of the historic WOW region and that such an overlap was statistically rare, only a few percent. No bold claims, no dramatic language, just a small, sober line at the bottom. Future interstellar visitors arriving from similar directions should be examined with special care. Atlas itself never spoke on the radio. It slipped through our system in electromagnetic silence. Yet that silence stirred an older echo, a brief, narrowband flare recorded in 1977 that still sits unanswered in the archives, like a question no one knows how to address. On October 29, 2025, observers weren't anticipating anything unusual. Routine scans of the inner solar system were underway when almost simultaneously data streams from Chile, Hawaii, and several spacecraft showed the same startling change. In a matter of hours, 3I Atlas had become about 5 times brighter. The rise wasn't gradual or noisy. It was abrupt and clean, more like a switch being thrown than a slow burn. Ordinary comets brighten as they vent. Ice turns to gas, dust is blown off, and sunlight scatters through the expanding cloud, producing a messy, warm-toned glow, yellowish, dusty, uneven. Atlas refused to follow that script. During its flare, its light shifted toward a cold, metallic blue. The spectrum looked less like sunlight sifting through dust and more like energized plasma, ionized, sharp, almost surgical. No fresh debris cloud appeared. No strong water lines joined the signal. Tianwen-1 and ESA's solar orbiter confirmed the same unsettling picture. The coma stayed eerily smooth, with no jagged edges, no obvious jets, no asymmetric wings. The object had brightened dramatically, but nothing obvious seemed to be thrown off. That single fact cut straight through standard comet theory. The energy had gone up. The mass, as far as we could tell, had not gone down. The first reaction was to blame machinery. Maybe one sensor had saturated, maybe a reflection had bounced into the optics, maybe cosmic rays had spiked a detector. Within hours, independent checks stripped those excuses away. Instruments using different techniques at different wavelengths and from different vantage points all recorded the same behavior. Atlas had genuinely flared, and it had done so by emitting light, not just reflecting more sunlight. One idea was that the solar wind briefly charged the object's surface, building a kind of plasma shell. Energetic particles could have excited a metallic skin into glowing, turning Atlas into a drifting capacitor that stored and then released electrical energy in the solar wind. Another possibility pointed inward, unusual transitions inside a dense, crystalline interior releasing energy outward in a controlled surge. Both concepts stretch the edges of current physics, but they fit the data better than the familiar dust and ice picture. Around the world, that night left control rooms unusually quiet. Atlas had already challenged our understanding of gravity and composition. Now it was forcing us to rethink what it means for a small body to shine. Its blue glow was not chaotic. It stayed remarkably stable, holding elevated brightness for almost 70 days before sliding back toward normal. No comet on record has ever maintained such a long, steady brightening without tearing itself apart. In the archives, the whole event was compressed down to 4 cool words: unexpected sustained photometric enhancement. Those who watched the live plots described it very differently. To them, the light didn't just brighten, it felt like it said something. The color had the character of deep space lightning, an electric blue suggesting hidden activity beneath a calm exterior. When the flare finally shut off as cleanly as it began, it left behind a singular spectral mark, a moment when the sky seemed to blink once in response. There's a simple rule that underpins most comet diagrams. When a comet is losing mass, you see it. The tail is the evidence, a pale glowing trail proving that material is being ripped away. Yet when 3I Atlas swept around the sun and appears to have shed roughly 13% of its mass, about 4 billion tons, no such signature appeared, no long ribbon of dust, no trailing gas streamer. Just the same compact halo, dim and rounded. From Earth's best telescopes and from orbiters circling Mars, the view was the same. The region opposite the sun, where any proper tail should have been pulled outward, looked empty. Even deep composite images, stacked to drag faint structures out of the noise, showed no trace of a lingering filament. Where physics told us to expect a blazing wound, the images showed unbroken dark. That absence cut directly into the mechanics. To produce the measured non-gravitational acceleration, Atlas had to fling mass away. A push requires exhaust, yet no exhaust was visible in the bands we were watching. The question hardened into a single line: if all that mass left, where did it go? Some proposed that the outflow might have been extremely hot. Extremely thin plasma radiating mostly in wavelengths our optical surveys weren't sensitive to, essentially invisible light. Others sketched more intricate possibilities. Charged particles forming a magnetic cocoon that bent the outflow in directions no one was pointing telescopes, or even redirected it back toward the object in a feedback loop. A few went closer to engineering territory, asking whether this could have been a propulsive maneuver. Mass expelled in a way intentionally optimized to generate thrust while minimizing visible traces. This anomaly felt different from the others. The blue flare was spectacular, the wow alignment was haunting. The missing tail was a void. Astronomers stared at high-resolution mosaics, knowing exactly where a luminous streak ought to be, and saw only pure background. That emptiness became a piece of data in its own right, a clean gap between what equations predicted and what the sky delivered. Official language kept its balance. No observable dust tail corresponding to the recorded acceleration, composition, or dynamics may differ from standard models. Between those lines, the deeper unease remained. If the tail is gone, so is the obvious proof. The very signature that should have confirmed the mass loss appeared to have been erased along with it. Atlas seemed to have carried out a major maneuver and then cleaned up its tracks. The metaphor many reached for was nautical. A ship crossing an ocean without leaving a wake, not because the sea was calm, but because the vessel somehow commanded the water to stay flat. Atlas hadn't only flexed the rules of motion, it had stolen the most iconic image we have for comets. A comet without a tail is like a voice without sound. Somehow, the quiet it left behind made more noise in the scientific community than any explosive outburst. When all the data were finally pooled together, 10 distinct anomalies emerged, each one improbable on its own. The reflex across most observatories was the same: there must be an error somewhere, not anger, not denial, just the disciplined instinct to doubt. Astronomy is built on careful suspicion. But as each oddity survived reprocessing and reanalysis and their separate probabilities were combined, the comforting cushion of coincidence began to thin. Each quirk had its own small chance. An orbit nearly lying in the ecliptic within about 5 degrees might be a 1 in 500 shot. A stable jet aimed toward the sun, fighting radiation pressure, might be a 1 in 1,000 event. A perihelion passage hidden exactly behind the solar disk from Earth's line of sight might be 1 in 20,000. When statisticians multiplied the odds of all 10 anomalies, even with conservative assumptions, the chance that they all appeared in one object strictly by luck dropped below 1 in 100,000, and in some models approached 1 in a million. That figure doesn't prove intent, but it does quietly suggest that just random may not be the whole story. At the Harvard-Smithsonian Center for Astrophysics, teams ran large simulations based on thousands of known comet orbits. None reproduced Atlas's mix of behaviors. In Europe, groups tried extreme outgassing models with violent spin and heating. None matched the sunward jet or the missing tail. At JPL, analysts combed through the acceleration data for subtle biases. The vectors stayed where they were, the extra push remained real. Only the mechanism was missing. Officially, the cautious view held: anomalies demand better models and more data, not leaps to extraordinary claims. In the catalogs, Atlas sits as an extreme outlier. Unusual, but not yet miraculous. Quietly, though, some researchers began to notice how the anomalies seemed to interlock rather than stand alone. The nickel-rich chemistry backed up the idea of a hardened metallic surface. The absence of a tail fit with tightly controlled mass loss. The sunward jet matched the concept of directional thrust, not random venting. One odd feature made the next more plausible. Isolated, each anomaly looked improbable. Taken together, they started to feel like parts of the same system. That's where Avi Loeb's perspective gained influence. He didn't declare Atlas artificial. Instead, he argued that it had to be taken seriously. When multiple low-probability features cluster around one object, he said, the responsible move is not to force them back into old categories but to broaden the set of possibilities. His call wasn't for belief, it was for intellectual humility: investigate without locking the answer in advance. That approach, expanding rather than tightening our assumptions, split the community. Space agencies stayed anchored to natural scenarios, exotic chemistry, unusual birthplaces, or rare erosion patterns. Behind closed doors, discussions sounded more open. At a closed workshop at the Max Planck Institute in late 2025, dynamicists, plasma physicists, and SETI experts met to compare notes. The confidential summary included one quietly revolutionary phrase: future work should proceed without presuming either a purely natural or purely artificial origin. Those two words, without presuming, became a quiet motto for a younger generation. For as long as anyone can remember, professional astronomy has carried an unspoken default: everything up there is natural. Atlas didn't automatically overturn that belief, but it did force people to ask why it is so rarely questioned. For many, this period felt like a small echo of the early quantum era, when familiar certainty dissolved into probability and paradox. Atlas, in its own way, perched at the edge between what we can measure and what we dare to interpret. Its refusal to fit easy explanations made both arrogance and wild speculation look equally lazy. Each failed attempt to fix the data became a reminder of how much room is left for surprise. By December 2025, one kind of consensus had formed: the observations were solid and the weirdness was real. Beyond that, agreement evaporated. The argument moved from what happened to what does it mean. Was 3I Atlas simply the most extreme natural wanderer we've seen so far, the cosmic equivalent of a rare roll of the dice made inevitable by galactic scale? Or was it the first hint of structure beyond our current frame, a sign that intelligence or some other organizing principle might leave traces in ways we haven't expected? The conservative explanation is still the official one. In that view, Atlas is natural, a statistical outlier produced by environments and processes we haven't yet sampled. Within a galaxy packed with stars and debris, events with a 1 in a million chance do happen. Pulsars once looked like artificial beacons. Gamma-ray bursts looked like weapons. Nature, every time, turned out to be stranger than our first guesses. From that angle, Atlas is a gift from chance, a physical sample of what rare extremes look like. If future discoveries show that it was unique, that will teach us one thing. If we find others like it, that will teach us something else. In science, rarity isn't a flaw, it's a signal that the universe still has corners we haven't mapped. What 3I Atlas did do, beyond any doubt, was change the way we look up. It passed through our system without sending a deliberate message, leaving behind no clear hello, only a trail of questions written in orbit plots and spectra. It reminded us that the universe doesn't explain itself neatly. It hands us riddles and waits to see whether we'll admit we're confused. We may never know for sure whether Atlas was a hardened child of chaos or the weathered fragment of something once shaped. But its visit left a mark. From now on, every unexpected flare, every odd trajectory, every new interstellar visitor will carry a slightly different weight. Not proof, but possibility. And that, more than any final answer, is what keeps people at the telescopes night after night. The sense that somewhere out there, in the data we haven't yet learned how to read, the next correction to our certainty is already on its way.